Welcome back, my learners. And let us now finish up the topic by looking at the volume scale factor. Having done something about the linear scale factor, which is which was vesseling up the area scale factor, but now it's a volume scale factor, abbreviated as V, talk of the ACF. How does a volume scale factor compare with the linear scale factor? Right, just a moment. What we had in the previous video, we saw that the linear scale factor, if that one is going to be squared, that gives us the what? Talk of the area scale factor. Now, what is it about the now linear scale factor versus the volume now scale factor? That is an issue because talk of the figure can have area, can also have what? A volume with the same one, sides. So what is the relationship? Corresponding sides of the two similar figures in terms of the volumes. How do we compare that? Right, now try to come up with a cuboid. You can decide the dimension of which in terms of height, length, and width, and we try to work up the volume of which. Right, so let's consider a cuboid. If I go and draw the sketch of which I may have it like this one. And I join this one, that one, and that one, and that, and that, and one. And the length of which, let it be to be first, let us have the width as a 4, this one should be length, or let's have this one length as a 6, width as a 4, and the height as a 3, a cuboid. Right, 4 centimeters, 6 centimeters, and 3 centimeters. So if I may try to ask you to find the volume of this cuboid, now it's about the volume, you'll be able to appreciate that's a volume of this cuboid. You talk of the area of the cross-section times the length. So area of the cross-section is, the cross-section is a rectangle, like so area of the rectangle times the length, or just simply talk of the length times width times the height, to take it simple. So here we talk of 3 times 4 times 6, right? When we multiply the values, we'll be in the position to calculate that, that's say 4 times 3, 12 times 6, that give us what? 72. This is now cubic centimeters. In the previous video, we are working out the areas, but now we are calculating the volume. The volume for this one is 72 square centimeters. Can you try now to enlarge so that we have to produce a similar object to this one? That's now an image. So let me enlarge this one by a scale factor of 2. So if I'll enlarge this one by scale factor of 2, what it means I'll have here, I'll have something that is very huge. But here, because of space, I'll just draw it as a sketch like this one here. But expect the dimension to be a little bit larger. Such that if talk of the length, it will no longer be 6, now it will be 12. Talk of the width here, it will now be 8. Talk of the height here, the height will be what? 6. So that's the kind of the figure we have. So if this one has been enlarged, then definitely it means this one you call it as the image, this one as the what? Object. And definitely the two figures has to be what? Similar. So here I've got two similar figures. Now let's try to work out the volume again for this figure, a resultant of enlargement. So the volume of this one, if we were to work out it, we can also do the same by that same formula. You talk over 12 times 8 times 6. And what you get out of that, you're going to get 576. 576 cubic centimeters. So what we have here, we have got two similar figures. This is the first one whose volume is 72, and the volume for this other one is 576. Now, let us do exactly what we did above the areas of similar figures, I'll need you to take the ratio of the corresponding sides. That is now a linear scale factor. Let us find the linear scale factor for this one and this one. That is the ratio of the corresponding sides. So what I have here, it means if I'm to work out the linear scale factor, that is LSF. This one should be, if this is my length and this is another length, then what I have is just like, say, if I talk of the ratio of the image to the object, image to object, then it would be 12 to 6, because this side corresponds to this side. And this one should be compared with the width. Here is 8 and this one is 4. So if you take the ratio of this one to that one, sometimes it will be the same, like the ratio of the what? Of the length, corresponding length. So this one, if you find that one, you find that this one is the same as the, you talk over 80 to 4. And this is the same as the ratio of the height, which is 6 to 3. Right. If you simplify, you get what? 2 to 1. Right. So simply, if we can try to analyze here, you'll be able to pick that, say, linear scale factor here is 2 to 1. Or you can write it as this way, 2 to 1. No problem. Right. But we always prefer writing like that, but it depends. You can write it in that form or that form. It's the same. Right. So which means the ratio of corresponding sides is always equal. When you talk of similar figures. Secondly, let us now work out the ratios of the volumes. That is now, we talk of the volume scale factor. What is it? So I've got only two volumes here, two values. Image to object. You'll be able to see what we get here. It's like we have got 72 versus 576. So the volume here, it will be 576 to what? 72. That's what we have. So ratio of the volumes is 576 for the larger one to 72 for the smaller cuboid. Right. So if we try to simplify, you'll be able to see that what we have in this case, when we try to simplify, you'll be able to realize that, say, if I simplify this one by a common factor, that's the HCF of the two values, you find that 72 gets here 8 times, or 72 is 1. Right. Ratio of corresponding sides of similar cuboid, 2 to 1. Ratio of the volumes is what? 8 to 1. Let us now compare as we did with the what? Areas in the previous discussion of the previous video. You'll be able to see that if I take the relationship to say how do the two ratios compare, linear scale factor and the volume scale factor, you'll be in the position to see that what is there is just like if I take the volume scale factor as 2 to 1, and that of the volume, and when I take the linear scale factor as 2 to 1 versus the volume scale factor as the talk of the 80 to 1, you be in the position that the two, if they are related, it means I have to take this one has to be cubed, or that one has to be multiplied 3 times. If this one is multiplied 3 times as much, that gives me the what? Volume scale factor. But for the area, it was just like the square. Right. So if I've got 2 to 1 multiplied 3 times, I'll get 8 to 1. So this one also tells us a story that say if I take the cube of the linear scale factor, then that is what? Volume scale factor. But that time it was just like when I take the square of the linear scale factor, that is the same as the area scale factor. So at least you find that somehow the two issues here are not hard to remember. The area, talk of the square, talk of the volume, talk of the what? The cube. So that is always true about it. So since the 2 to 1 is represented by L, that talk of the SCF, and this one 8 to 1 is represented by V SCF. Then we made use here to say linear scale factor, the cube of the linear scale factor is equal to the volume scale factor. Or vice versa, you'll be able to analyze it out. If you'd like to find the value of the linear scale factor, that should be the what? Cube root of the volume scale factor. So that one simply means that or if not want to do that one, it means linear scale factor, that should be cube root of volume scale factor. That's it. So this is what you are supposed to know. Right. So for this, I'm very happy that we have done everything about the ratios. Right. What I have last maybe is just that amount of practicing on how we can use this ratio of the linear scale factor versus the volume scale factor. Right, now having done something about this one, that now we are very conversant about the volume scale factor in relation to the linear scale factor, can we now have a practice problem that will help us to understand this one better, as to say how do we use this relationship to work out the problems. So let us have this example. Right, think one is enough. So if you are copying, please also do so. Okay, all right, here we just have good and more of a direct example where we are given that the volume of two similar cylinders, that's about similar cylinders, are 198 and the 5,346 cubic centimeters. If the radius of the smaller one is 3 centimeters, can find the radius of the larger cylinder. Right. So all the tactics are as what was already introduced in the area scale factor. So here we're going to have the same approach. But what differs is only that here we're working on the volume scale factor. So if maybe I'm to produce the two shapes here, you'll be able to realize that we have two shapes. One is smaller cylinder, which is this one, and the other one is almost large. Right. So just to give you a tentative understanding what is there about the two cylinders. Right. So here the volume of this one, V, is given as 198 cubic centimeters, but the volume for this one is equal to, that is the 5,346 cubic centimeters. That's what we have. And now we are told that the radius of the smaller cylinder, the radius here can talk of any distance from the circumference of the circle on the circular end, base or the up there, because the two opposite faces are just the same. Then you can talk of here is 3, and the radius of the other is not known. So you can let it be what? Be x. So that's it. Yeah, radius 3, radius is unknown. Volume is 198, volume is 5,346. Status of the two cylinders are similar. So in this case, you always there about the relationship. That is there about the linear scale factor and the volume scale factor. That knowledge will help you to work out the missing variable. In this case, is x, representing the radius of the larger cylinder. Right, so without wasting time here, is all what we did about the area. So in this here, you are going first of all to compare, to say, if I would like to find x, I can use the knowledge above the comparison between the area scale factor, and the volume scale factor and the linear scale factor, of which the relationship, as already highlighted, is talk of the cube of the linear scale factor is equal to the volume scale factor. So you can use that knowledge to find the value of the talk of the radius of the larger cylinder. So how you go about this, like you bring in this relationship as such, talk of the linear scale factor, you substitute for the values in the equation and also the volume scale factor. Right, so how you begin here is more like the same as introduced in the previous video when working issues about the area, to say we have to let the talk of the radius over larger cylinder be equal to x. Right. So what we're going to do in this case, we are going to have our linear scale factor represented as what? Talk of the x to 3, beginning with the larger talk of the cylinder, C radius, compared with the what? That's the smaller cylinder. So talk of the linear scale factor talk of x to 3. While on the other hand, we are to talk of the volume scale factor, right? This one is also going to be compared by the volumes themselves of the two similar figures. So here volume of the larger one is 5346, the smaller one is 198. So since here in lighting the linear scale factor, we've studied the larger radius to the smaller radius. We also do the same way. It means we begin with the larger talk of the volume. If we are to introduce the ratios, that is 5, 3, 4, 6 to talk of what? That is 198. Right. Once we have done this, you're now going to compare the two ratios, the linear scale factor versus the volume scale factor. So from what we have just been introduced in the previous, just to go to shortly, you will be able to see that, say, if we compare the linear scale factor and the volume factor, it's just like when you cube the linear scale factor, that gives you the volume scale factor. That's it. So I'll bring an equation of that kind as the x to 3 cube is equal to 5346 to 198. That's it. So you can see how the comparison between the two ratios are being used to find the value of the unknown. In this case, is the radius. So that once this one is done, then now we can proceed now working out the value of x from this equation. So in this equation, right, so you do just have to find the value of x. Right, so let's now do it together and see how we can isolate x, right, which is the radius in this case. So what we have from that, it will be like if you pick up from this stage, it means we have got x to 3 cube is equal to 5346 to 198. So what I'll do here, I'll just use simple calculations, that's the arithmetics, in whatever way you like. You can find the value of x. One can begin by taking the cube of this, where you have got one talk of the x to the power 3 over 27 is equal to that, or else what you need to do, you can divide this one into that, anyway around, but at the end, you should find the value of x, and whatever process you do are mathematics, so there's no problem there. Right, so in my case, I'll choose first of all to simplify this part, where I'll have my x over 3 here, cube, and I'll have 198 getting to this one. I'll find that this 198 gets into 5, 3, 4, 6, 27 times. So it means this gets there, is it 27 times. So when I write 27, it's as good as writing 27 over 1. That's why it is there. Right. So now, what is it that I should do? let him isolate x, right? So x is part and parcel of the fraction here of the x over 3, and it's inside the bracket which has got the power 3. So to remove the power 3, I need to take the cube root on both sides. So cube root of this side here, it will be equal to x over 3, and cube root of that one here, it will be, that is now cube root of 27 over 1, it will be equal to 3 over 1. Right, so what we have in this case, it will be like a situation that looks something like this. You talk of x over 3 is equal to 3 over 1. Right, from that stage, you can just cross multiply 1 times x and then 3 times 3 to find the value of x. Right, so in this case, what it means, we have got x times 1, I've got x here, and 3 times 3, we have got 9. So x is equal to 3, which means the radius of the larger cylinder must be equal to 9. So we concluded that to say, therefore, radius is equal to 9 centimeters. That's all. Right, so that's the way you were supposed to handle this problem here. Comparison just between the two ratios, linear scale factor and the volume scale factor. Right, wish you all the best. There are several problems that you can use in practicing the issues about the ratios for both the area factor and the volume scale factor. Check the several books. You can use talk of the Chikwakwa Fabit. You can also have a book about the Excel and Succeed. So many books, you're going to find these questions. So please, for your own goodness, can you try to practice, solve so many of them, and then you update your mind and be knowledgeable about the area and volume scale factor. All in all, that concludes our topic. Light has been short, and by that, in the other video to come, we'll be introduced in another new topic, and this one will be coordinate geometry. Thank you very much. But do not forget always to be updated by the link that is down here for all the videos we have had. Thank you.